welcome back to my channel. Today we will be learning about how AVL trees maintain balance in binary search trees using rotations. We'll cover balance factors, node topologies, different types of rotations, and the code implementation behind AVL balancing. AVL trees are very important in data structures because they help maintain fast searching, insertion, and deletion operations. So without further ado, let's get right into the video. So what is an AVL tree? An AVL tree is a self-balancing binary search tree, also known as a BST. The name AVL comes from its creators, Anderson, Belsky, and Landquist. In a normal BST, if values are inserted in sorted order, the tree can become skewed like a linked list. That makes operations slower. AVL trees solve this problem by automatically balancing themselves after every insertion and deletion. The important rule is the height difference between the left and the right subtree of any node cannot be greater than 1. Because of this balancing, AVL trees maintain efficient or log-n performance. Without wasting time, let's understand what is the balance factor in VSTR. To determine whether a node is balanced, AVL trees use something called the balance factor. The formula is balance factor equals height of left subtree minus height of right subtree. If the balance factor is 0, the node is perfectly balanced. If the balance factor is 1 or negative 1, the node is still balanced. If the balance factor is greater than 1 or less than minus 1, the node becomes unbalanced. For example, if the left subtree height is 3 and the right subtree height is 1, the balance factor equals 3 minus 1, which is 2. That means the node is unbalanced and requires rotation. So why do we need rotations in AVL trees? Whenever new nodes are inserted into the AVL tree, the structure can become unbalanced. If the tree becomes too skewed, searching becomes slower, insertion becomes inefficient, and the binary search tree loses its performance advantage. Rotations are operations that rearrange nodes while still maintaining BST properties. Their main purpose is to restore balance and reduce tree height. This allows AVL trees to continue performing operations efficiently in all log-n time. Before learning rotations, we first need to understand topologies. A topology refers to the shape formed by nodes when imbalance occurs. The first topology is the straight leg. This happens when nodes form a straight line either towards the left or towards the right. This usually causes left-left or right-right imbalance. As you can see in the picture, this has go to the left side. This can also go to the right side. And the second topology is the dog leg. This creates a zigzag pattern. This causes left-right or right-left imbalance. As you can see in the picture, this has go to the right-left or left-right. The third topology is the spider leg topology. This is more of an informal term used to describe deeper or more complex imbalance patterns involving multiple levels. As you can see, this is the first level, this is the second level, this is the third level, and the fourth level. Understanding these shapes helps us identify which rotations should be used. So now let's look at the left-left rotation, also called AVL rotation. This happens when insertion occurs in the left subtree of the left child. For example, suppose we insert 30, then 20, then 10. The tree becomes left-handed. Before rotation, 30 is on the right, 20 is on the left, and the 10 is on the left of 30, left of 20. This creates imbalance at node 30. To fix this, we perform a right rotation on node 30. After rotation, 20 becomes the new root, 10 becomes the left child, and 30 becomes the right child. The AVL tree becomes balanced again. Next, I'm going to be explaining right-right rotation, or RR rotation. Is the opposite of AVL rotation. This happens when insertion occurs in the right subtree of the right child. For example, insert 10, 20, and 30. The tree becomes right tail. Before rotation, 10 is the root, 20 is its right child, and 30 is the right child of 20. To restore balance, we perform a left rotation on node 10. After rotation, 20 becomes the new root, 10 becomes the left child, and 30 becomes the right child. The AVL tree is balanced again. So now I'll explain what left-right rotation is, also known as LR rotation. This happens when insertion occurs in the right subtree of the left child. For example, insert 30, 10, and 20. This creates a zigzag or a dogleg pattern. A single rotation cannot fix this imbalance. So ABA gives us two rotation. Step 1. Perform left rotation on node 10. This converts the structure into a left-left case. Step 2. Perform a right rotation on node 30. After these two rotations, 20 becomes the new root, 10 becomes the left child, and 30 becomes the right child. The tree becomes balanced again. The final rotation is the right-left rotation, or RL rotation. This happens when insertion occurs in the left subtree of the right child. For example, insert 10, then 30, then 20. This again creates a zigzag structure. To fix it, AVL trees perform two rotations. Step 1 is to perform a right rotation on node 30. This converts the structure into a right-right case. The step 2 is to perform a left rotation on node 10. After balancing, 20 becomes the new root, 10 becomes the left child, and 30 becomes the right child. The AVL tree becomes balanced once again. Here I have a simple code implementation for right rotate and left rotate. Here I have the right rotation function. Right rotation is mainly used for left-left imbalance. First, the left child of y is stored in x. Then the subtree t2 is temporarily stored. Next, x becomes the new root, y moves to the right side, and t2 is attached to y. Finally, the function returns x as the new root after rotation. This restores balance in every tree. So the next one is the left rotation function. The left rotation function is mainly used for right-right imbalance. First, the right child of x is stored in y. Then the subtree t2 is temporarily stored. Next, y becomes the new root, x moves to the left side, and t2 is attached back to x. Finally, the function returns y as the new root after rotation. This rotation restores balance while maintaining the binary search tree structure. And that brings us to the end of this video. Today we learned how AVL trees maintain balance using balance factors and rotations. We discussed the different node topologies, including straight leg, dog leg, and spider leg structures. We also learned about the four main rotation types: left left, right right, left right, and right left rotations. Finally, we looked at the basic code implementation of AVL rotations and understood how these functions help restore balance in the tree. AVL trees are important because they maintain efficient searching, insertion, and deletion operations by preventing the tree from becoming unbalanced. I hope you'll enjoy this video and learn something new about AVL trees and rotations. AVL trees are an important part of data structures because they help maintain efficient and balanced searching operations. If you would like to learn more about AVL trees and rotations, I have included the website and references I used to gather information for this video. And thank you again for watching, and I'll see you guys in the next video.